Hello and good morning. My name is Irfan Shariq bin Saidan. I'm from class RS 2034A, and in this video, I will be talking about test and analysis on thermal expansion behavior of steel strand used in the pre-stressed concrete structure under low temperature. The article were made by Jian and Jia Boyan, and the paper was accepted in 7 January of 2018. Jian is a PhD candidate in economics at the University of Warwick. His current research investigates AI innovation, family firms, and the impact of the reform of state-owned enterprises. He is also interested in entrepreneurship, people's attitude towards AI, and the role of culture in economic development, fertility, and human capital accumulation. While Jia Boyan is a researcher at Tianjin University, his interests include steel structure, steel concrete composite structure, and reinforced street structure. Recently, as the needs on oil and gas keep increasing, the exploration of the oil and gas has been extended to the Arctic region, since this region stores 30% of the world's undiscovered oil and 30% of gas. Different types of offshore and onshore platforms will build for the exploration of the oil and gas. Most of these Arctic engineering construction were made of reinforced concrete, RC, or pre-stressed concrete, PC. During their service life, all these PC or RC structure suffer harsh environment with low temperature. Another scenario of the PC or RC structures under low critical temperatures occurs to the container for the liquid natural gas or LNG. Due to the increasing consumption of the LNG, more and more PC LNG containers have been built and put into use. Since these RTRC or PC structure and PC LNG containers were exposed to the low temperature, the mechanical properties of the steel strand used in the RC or PC structures need to be carefully determined for the evaluation on their structural performance. Before we go any further, I want to explain a little bit about PC and RC. Pre-stressed concrete is a system devised to provide sufficient pre-compression in the concrete beam by tension steel wires, cable, or rods that under working condition, the concrete has no tensile stresses, or the tensile stresses are so low that there are no visible cracking occurs. While reinforced concrete is a concrete in which steel is embedded in such a manner that the two materials act together in resisting forces. The reinforcing steel rods, bar, or mesh absorb the tensile, shear, and sometimes the compressive stresses in the concrete structure. There are two main objectives in this experiment. The first objective is to obtain the necessary information on strand thermal expansion behavior under low temperature levels and pre-stressing levels. And the second objective is to analyze the structural behavior of RC and PC structure with steel strand under combined low temperature and different loading scenario. This test program adopted a 7-wire strand that was widely used in the PC structure. The geometric and mechanical properties of the steel strand include the diameter of the strand is 15.2 mm, the length of the steel strand is 1000 mm, the yield strength, elastic Young modulus, and fracture strength of the strand are 1860 megapascal, 168 gigapascal, and 0.05 respectively. The ultimate tensile resistance of the strand is 264.2 kN. Considering different pre-stressing levels influence the thermal expansion coefficient, 5 pre-stressing levels were applied to the steel strand specimen. Thus, the specimen can be categorized into 5 groups, namely level that was reserved for the test before the cooling process. After the pre-stressing on the strand, liquid nitrogen was injected to the cooling chamber. 6 thermocouples were variously distributed on the surface of the steel strand to monitor its temperature. After achieving the target temperature of -165 degrees Celsius, the injection of the liquid nitrogen will be controlled to maintain this temperature level. Then, the steel strand was pre-stressed to the target pre-stressing level, and this pre-stressing level was maintained during the thermal expansion behavior test. After that, the temperature in the cooling chamber will be gradually increased to the ambient temperature step by step. During this heating process, linear varying displacement transducer LVDT were used to monitor the displacement at the two ends of the steel strand as shown in the figure 1. All the reading of the sensors, including the thermocouples, load cell, and LVDT, were monitored and recorded by software running on the PC during the testing. And each group contains 3 identical specimens. The testing procedures on the thermal expansion included the cooling process, maintaining process, loading, and measuring process. In order to realize the simulation of the low temperature testing environment, a cooling chamber was used. Figure 1 shows the test setup for the coefficient of the thermal expansion of the steel strand under combined different pre-stressing level and low temperature. Liquid nitrogen was injected into the cooling chamber through an electromagnetic valve to achieve the low temperature environment. Insulation measures were taken to cover the cooling chamber to isolate the heat transfer from the environment to the cooling chamber. Since the pre-stressing level would provide an influence on the thermal expansion coefficient of the steel strand, hydraulic jack was used to pre-stress to the strand in the cooling chamber. During each test, the steel strand was firstly put into the cooling chamber and installed on the reaction frame. Followed, pre-stressing was carried out to the steel strand by the hydraulic jack. Considering the contracting stress due to low temperature, a gap of 30 kN to each target pre-stressing level was reserved for the test before the cooling process. After the pre-stressing on the strand, liquid nitrogen was injected into the cooling chamber. 6 thermocouples were variously distributed on the surface of the steel strand to monitor its temperature. After achieving the target temperature of -165 degrees Celsius, the injection of the liquid nitrogen will be controlled to maintain this temperature level. Then, the steel strand was pre-stressed to the target pre-stressing level, and this pre-stressing level was maintained during the thermal expansion behavior test. After that, the temperature in the cooling chamber will be gradually increased to the ambient temperature step by step. During this heating process, a linear varying displacement transducer LVDT were used to monitor the displacement at the two ends of the steel strand. All the reading of the sensors, including thermocouples, load cell, and LVDTs, were monitored and recorded by software running on the PC during the testing. Figure 3 shows the thermal strand versus the temperature relationship for the steel strand under different pre-stressing levels. These figures show that there are 2 working stages for the development of the thermal strand as the temperature increases from -165 degrees Celsius to 0 degrees Celsius. At stage 1, temperature interval from -80 to 0 degrees Celsius, the contracting thermal strand increases almost linearly with the increase of the temperature. At stage 2, temperature interval from -165 to -80 degrees Celsius, the thermal strand increases non-linearly with the increase of the temperature. This non-linear behavior may be caused by the change of the microstructure of the steel strand under low temperature below -80 degrees Celsius. Secondly, these figures also show that the thermal strand increased with the increase of the pre-stressing forces applied on the steel strand. Figure 4 plots thermal strand of the steel strand under certain temperature levels with different pre-stressing forces. it can be seen that at a certain fixed temperature, the thermal strength of the steel strand increases almost linearly with the increase of the pre-stress in the strand. This is because that the pre-stressing accelerates flow of metal as well as the temperature dies. This is the transit linear expansion coefficient that we use to describe the thermal expansion at a certain time point. The transit linear thermal expansion coefficient of three identical specimens are listed in the table 2. These figures and table shows that 1. The transit linear expansion coefficient of the steel strand increases almost linearly with the increase of the temperature. 2. The transit linear expansion coefficient exhibits strong correlation with the low temperature. For example, the correlation coefficient of R square are larger than 0.5, and in some cases, the R square values are even close to 0.9. And thirdly, the transit linear thermal expansion coefficient increases with the increase of the pre-stress applied in the steel strand. This is because the low temperature reduces the molecular translational energy that reduces the activity of atomic, and more molecular translational energy will be required for the heat transfer, which result in the reduction of the transit linear expansion. From the article, there are two conclusions that we can make is that 1. Increasing the pre-stressing stress applied on the steel strand leads to the increases of both transit and average linear expansion coefficient of the steel strand under low temperature. And 2. The decrease of the temperature from 20 to minus 165 degrees Celsius significantly reduce the transit and average linear expansion coefficient of the steel strand. That's all for this video. I hope that you learned something new in this video, and thanks for watching.